Great. Yeah, so excited to talk about joint work with Jordan Cotler, Robert Huang, and Jerry Lee on the complexity of NISQ. All right, so as we all know, we're still many years and a couple engineering breakthroughs away from actually implementing fault-tolerant quantum computation. So in the meantime, there's been a lot of excitement around the various platforms for noisy quantum computation that are currently available in the NISQ era. And typically in the NISQ era, algorithms for these kinds of devices are based on sort of an interactive procedure between a classical computer and some kind of noisy quantum device. So you can imagine maybe the classical computer is trying to train some variational model. It can update parameters based on maybe gradients information that you get out of the noisy quantum device. But in general, you're not going to be able to get mileage just out of using the noisy quantum device alone. You need some kind of hybrid between the two resources. Okay, and so there have been a number of different algorithms proposed and developed for these kinds of near-term devices, there's a lot of promise in solving various problems in quantum chemistry, machine learning, experimental data analysis, etc., using these sorts of algorithms. In this work, we're going to take a different tack. Instead of considering any particular algorithm in isolation, we're going to ask, if I consider the union of all possible algorithms I could run using a near-term quantum device, what is the inherent computational power that's captured by this class? Okay, so really, this is the complexity session, so we're really going to look at this through a complexity theoretic lens. And we're going to try to understand, there's some complexity class that seems to sit in between BPP and BQP that's captured by these algorithms, and we want to understand, is it truly intermediate between these two classes? Can I find interesting questions for which I get nice speedups over classical computation? Are there certain inherent limitations to using these noisy algorithms versus using fault-tolerant quantum computing? Okay, so we need to formulate some definition, and so ideally this definition should capture common features across the majority of existing noisy devices. Okay, so for starters, of course, we're going to assume that we can only sort of execute noisy quantum logic gates. This seems fairly reasonable. The second desideratum that we want is that instead of being able to introduce like fresh ancilla in the middle of the computation, we're going to assume all of our qubits are prepared at the start. Okay, and the motivation is that the devices we're considering have a fixed number of qubits. All of these qubits are going to accrue entropy over the course of the computation. And you're not going to sort of be able to pump out entropy by introducing fresh initialized qubits in the middle. Okay, and the last feature that we want out of this definition is that it's supposed to capture the notion that we can only make some kind of measurement across all qubits at the very end. Of course, this measurement will have noise, but the main point here is that you're not allowed to make intermediate measurements in the middle. Okay, and this is really just for practical reasons. It turns out to be difficult to really isolate qubits in the middle of your computation to measure without ending up decohering the remaining qubits. Okay, so these are the three features we want out of our definition. Removing any one of these already allows for non-trivial fault tolerance. Okay, so with these in mind, let's define our complexity class. So a NISQ algorithm, we're going to allow to make queries to a particular oracle that I'll refer to as an NQC oracle for the rest of the talk, just a noisy quantum circuit. Okay, so the idea is, the classical algorithm can pick some sequence of unitaries, U1 through UT, and then give this to the oracle, and the oracle is going to spit out some sample from a distribution over classical strings. Namely, the distribution you get if you run this noisy quantum circuit using the sequence of unitaries, and then measure the result on the computational basis. So here's a picture. I initialize with all zeros. I have the sequence of unitaries. I measure at the end, but in between each layer of computation, I have local noise. Here, D, you can think of for concreteness as maybe like single qubit depolarizing noise at some rate lambda from 0 to 1. But more generally, our upper bounds can tolerate more general forms of local noise. Okay, so this is really capturing not just noise in the unitaries that you're applying, but also in the state preparation at the beginning and in the measurements. Okay, so then what does a NISQ algorithm look like? This is really just a probabilistic Turing machine that can make arbitrary queries to this NQC oracle. Okay, so it applies some classical computation at the beginning to decide what circuit to run. Then it runs that circuit using the oracle. Based on whatever classical string it sees, it does some further classical post-processing. It decides, okay, I'm going to run some other circuit, etc. And ultimately, the runtime of this algorithm is going to be dictated both by the total classical runtime of this Turing machine and also the time spent on these NQC queries. Okay, and we're going to measure the time spent on the Oracle queries as really, essentially the product of the depth and the width of each given circuit. Okay, so if it's querying unitaries U1 through UT over some number of qubits, let's say, M, then we think of the runtime of that particular Oracle call as scaling roughly as M times T. Okay, and so now we're ready to define our complexity class. This is just the class of all languages that are accepted by a polytime NISQ algorithm with high probability, where here polytime refers to this this runtime defined here. Okay, so I've already alluded to the answer to this, but you might be asking, why isn't this just BQP by the threshold theorem? And the reason is that because we've constrained the NISQ algorithm to not be able to initialize fresh ancilla in the middle and also not make partial measurements, this precludes all known fault-tolerant schemes. And one conceptual takeaway from this is really we're defining a complexity class, so we allow the input size to go to infinity. So it's not really the scale of these devices when it comes to the number of qubits available that's really the bottleneck. Somehow it's the thing that separates NISQ from BQP intuitively is this inability to pump out entropy. You're not by not allowing you to initialize fresh ancilla or make partial measurements, you're really carrying this entropy across the course of the entire noisy quantum circuit call. And somehow, as we'll see, this introduces really very concrete barriers to getting interesting quantum speedups. Okay, so here's the outline for the rest of the talk. I'm going to begin with two well-known, well-studied problems: the classic Bernstein-VAZIRANI problem and also unstructured search. And I'm going to show both speedups and slowdowns when it comes to NISQ. I'm then going to turn to more general sort of super poly separations between BPP, NISQ, and BQP relative to certain oracles. Time permitting, I'll mention a bit about shadow tomography, and then I'll conclude with some open problems. Okay, so let's start with Bernstein-VAZIRANI, and this one is fairly clean. All right, so recall in Bernstein-VAZIRANI we have some unknown linear equation mod 2, specified by some vector in Z2n, we'll call it S. Okay, and what we show is that with the NISQ algorithm, you can actually still solve the Bernstein-VAZIRANI problem with high probability using essentially log and n many Oracle queries. Contrast this to the sort of separation that we know for BPP versus BQP, where classically you'll need n Oracle queries to solve a linear system over Z2n. In contrast, quantumly constant many queries suffice. Okay, but the takeaway here is that NISQ actually exhibits an exponential advantage for this particular problem, and in fact the algorithm is just a minor post-processing on top of the original Bernstein-VAZIRANI algorithm. Okay, so here's the classic Bernstein-VAZIRANI algorithm, right? So the idea is you prepare the all plus state in the first n qubits and the minus state in the ancilla qubit. You make an Oracle query, then you Hadamard the first n qubits and measure. And the point is that the state that you have right after applying the Oracle among the first n qubits is of this form, so that if I then Hadamard a measure, I get out exactly the unknown string S. Okay, so now how does the picture change when I introduce local noise everywhere? So for simplicity, let's pretend that actually the ancilla qubit never gets corrupted over these 4 layers of noise that I've labeled. Okay, and this happens with pretty high probability. If your noise rate is lambda, this happens with probability 1 minus lambda squared. Okay, so now let's consider which qubits among the first n qubits get corrupted across the 4 layers of noise. Okay, so it defines some partition of the first n qubits. And now let's look at the, again, the state right after I've applied the Oracle, but restricted to just the uncorrupted qubits. And you can check that you get something very similar, right? So you also get this kind of Fourier transform at the frequency S of the unknown string, but now instead of the entire string S, it's confined to just the bits of the string which are uncorrupted. Okay, so now if I Hadamard a measure, I end up with just the substring of S corresponding to the qubits that weren't corrupted. Okay, so the takeaway is that if a particular qubit I is never corrupted in any of the 4 rounds of noise, and furthermore the ancilla is not corrupted, then when we measure that particular qubit at the end, we get the correct bit value. Okay, and the probability this happens, well, there are 4 layers of noise, and then there are also the 2 layers of noise applied to the ancilla for a total of 6 events. And so this is going to happen with probability 1 minus lambda to the 6th. When lambda is a sufficiently small constant, things are fine. And so the algorithm is very simple. You just run Bernstein-VAZIRANI many times and apply a majority vote to each bit to figure out what this underlying string is. So this is super simple. And it's just sort of like a warm-up to show you that you can get interesting speed-ups even in NISQ. But this might not be super surprising because Bernstein-VAZIRANI is a very low-depth algorithm. What happens now if we turn to a higher depth setting, like Rover search? Okay, so here we show that actually you don't get any meaningful speed up once you have constant noise rate. So we show that for Grover search over n elements, any NISQ algorithm with access to poly n qubits requires at least linear in n times lambda number of queries up to log factors. And the log factors are mostly an artifact of the analysis. What this is really saying is that with constant noise rate, you don't get any kind of speed up over classical. Okay, so how do we prove this? All right, so we're going to use this sort of learning tree formalism that's been pretty useful in proving lower bounds in other settings where you're trying to learn from quantum data with so-called incoherent measurements. So in general, this learning tree formalism says, like, I have some NISQ algorithm, and I can encode it as some kind of decision tree, right? So every node in the decision tree is some NQC call. And you branch off in the tree based on, what is the classical string that you observe after that particular oracle call. Okay, so you can think of any realization, if I run this algorithm once, I'm going to get some path through this decision tree. And the oracle is going to define ultimately some distribution over paths, and equivalently a distribution over leaves of this decision tree. Okay. And based on this distribution, you're going to get different behavior for the algorithm. Okay, so let's look at the following set of possible distributions over the leaves. Let's define Q to be the distribution over leaves if the oracle is actually the identity. And let's define P sub I to be the distribution over the leaves when the oracle is the ith Grover oracle. And so to prove this lower bound, all I have to show is that essentially no algorithm can, given a draw from Q versus a draw from P sub I for a random I, no algorithm will be able to distinguish between which of these 2 situations you're in. Okay? So equivalently, you need to show that the total variation between Q, this distribution when the oracle is identity, and expectation over I of P sub I is negligible. Okay? So here's the strategy. The idea is, okay, first we're going to formalize this notion that NISQ algorithms can essentially only implement bounded depth computation. And once we've reduced the bounded depth computation, we're going to prove a lower bound against low depth quantum circuits, even in the absence of noise. Okay, and that's the whole proof strategy. So the first step is actually fairly standard. Okay, so the reason you can assume all of your noisy quantum circuit oracle queries are low depth is this old result of Aronov and others that says that, let's say I have some quantum circuit of depth T, okay, and let P be the distribution over output strings. It turns out that the KL between P and the uniform distribution over strings is exponentially decaying in the depth of the quantum circuit. Okay, so as I run the circuit for longer and longer, I sort of lose any meaningful information about from this computation. Okay, so the point is, if I take T now to be roughly logarithmic in n, then the KL is going to be scaling with 1 over poly n, which means now if I take every part of my algorithm where I used a large depth NQC call, and I replace that with just a draw from the uniform distribution, I'm not going to move the distribution over leaves by too much in statistical distance. Okay, so this is really formalizing the fact that I can just sort of take all the instances where I used high depth computation and just throw them out the window. Like they're not giving me any meaningful statistical information. Okay, so that's the first step of the proof, and the second step is I owe you a lower bound when all of my Oracle queries are actually low depth quantum circuits. Okay, so I want to bound this TV between these two distributions. Equivalently, one way to do this is to show that the likelihood ratio between these two distributions is always close to 1 with high probability. And the idea for doing this is if you look at this sequence of likelihood ratios between pi and q for the first, let's say, s iterations, this sequence is actually a multiplicative martingale, which means that if I look at the multiplicative jump when I go from the sth step to the s plus first step, in expectation that multiplicative jump is 1. Okay, I want to use this an off-the-shelf martingale concentration to then show that this quantity ends up being very close to 1. And for this, I need to control the variance of these multiplicative jumps. And it turns out the variance is actually controlled by this square distance between the following two states. One is the output state under a particular quantum circuit when the underlying oracle is the ith Grover oracle. Okay, that's phi I of A. And phi 0 of A is the same thing, but when the underlying oracle is the identity. Okay, so this is a quantity that people have studied a while back. We know actually that this quantity on average over I is bounded by roughly t squared over n. Okay, and what that tells us, the variance is at most t squared over n, which means on average the multiplicative jumps are 1 plus or minus t over root n. Remember, t is some logarithmically large quantity, so this is morally something like 1 plus or minus 1 over root n, which means after roughly n steps, the likelihood ratio is still going to be 1 plus or minus little o of 1. Okay, so that's the whole proof. I should mention that there's another work by Sun and Zheng that showed a very nice negative result that's of the same flavor, showing that for hybrid quantum classical with bounded depth quantum computation, you get the same kind of lower bound, but they use a very different set of tools, namely the adversary method. I think it's quite interesting to see what are the sort of connections between this likelihood ratio method and the adversary method. Okay, let me talk briefly about the BPP versus NISQ and BQP. Okay, so we're going to show some oracle separations among these three classes based on variants of Simon's problem. So recall Simon's problem, you have some 2-to-1 function from n bits to n bits. This function is periodic, and there's some unknown period, which we'll call S. Okay, so our two results along these lines are oracle separations among these classes relative to two variants of Simon's problem. To separate classical computation from NISQ, we use sort of a robustified version of Simon's oracle. And to separate quantum from NISQ, we use a non-robust version of Simon's oracle. Okay, so I think in the interest of time, I'll just talk about the non-robust version of Simon's oracle because it's fairly simple to describe, and then I'll conclude with some open questions. Okay, so here's a cartoon for a 2-to-1 function. So how do we separate quantum computation from NISQ? We're going to take this 2-to-1 function and lift it into a higher space. So this should be reminiscent of this kind of like shuffling Simon's problem, if you've seen it before, that's used to, in this nice paper on the need for large quantum depth. Okay, so we embed the n-dimensional hypercube into the 2 n-dimensional hypercube, and then for all remaining strings, we simply send them to 0. Okay, and then the idea is simply that if I take some interesting input and apply some noise to it, I'm going to end up in this uninteresting region, which just gets sent to 0, with all but exponentially small probability. Okay, and that's essentially the whole proof. Like, it's saying that the noise, really kills all of the signal that you have. Okay, so this is like the simple direction, or one of the simpler of the two separations. I feel like I don't have much time to talk about the other one, so I'll conclude with some open questions. But yeah, so again, like this, you can play around with this lifted instance and use the shuffling Simon's problem to actually get a stronger separation between NISQ and BPP to the QNC 0. Okay, so let me just skip to the end. Okay, I don't know. All right, this was Okay, so let me just mention some open questions because I think there are a lot of exciting directions that people in the audience are poised to be able to make some cool progress in. So one basic question is, are there more natural oracles? So I didn't actually mention the robustified oracle that we use to separate BPP from NISQ, but it's we're essentially wrapping Simons into around with an error correcting code. Ideally, there should be some nicer way of getting the separation. You could conjecture maybe you can actually separate them relative to a random oracle, but we conjecture this is not possible. You could also ask for an oracle that simultaneously separates all three classes rather than having a different variant for each direction. Can you show a NISQ lower bound separating BQP and NISQ just using vanilla Simon's problem? Can you modify the complexity class definition to incorporate spatial constraints, or even incorporate a modest amount of partial measurements or intermediate Ancilla initialization? And of course, the $1,000,000 question is, what other speedups can you hope for beyond Bernstein-VAZIRANI? And just to philosophize for a bit, I think it's one reason I like this direction is that it's really a unique chance for complexity theorists to really study a complexity class that's directly motivated by contemporary engineering constraints. And just to summarize, with this philosophy, we define this complexity class that kind of gives you a way to rigorously reason about noisy quantum advantage. We give some oracle separations and upper and lower bounds for well-studied problems, but I think there's a lot more to explore in this direction. So yeah, thanks for listening.
Questions?
Maybe I missed this during your talk, but is there some kind of bound on how noisy your gates and preparation and stuff can be? Because I'm kind of thinking, if it's too noisy, then I think I've seen some papers saying that once you get past a certain noise bound, then you should be able to classically simulate any quantum circuit. But then in a similar kind of contrast to that, if you make it arbitrarily small amount of noise, say your error is 1 on, I don't know, e to the n times 1,000,000. Then I'd imagine that you'd get almost exactly BQP in anything we really care about. Can you talk about that?
Yeah, definitely. I guess the summary is just that we mainly consider a regime, for instance, where the noise can be some arbitrarily small constant. So if you think of this Grover lower bound, for instance, you see that there's a scaling of n times lambda. So for instance, you can imagine lambda maybe as some like slightly subconstant, like inverse polynomial, and you still get a lower bound separating between NISQ and what you could do with full BQP. Similarly for Bernstein-VAZIRANI, as long as the noise is at most some fixed constant, you get the speed up for Bernstein-VAZIRANI. So for the different, and in general, like for these oracle separations, similarly, like as long as you have some small constant amount of noise, like all the results apply. There's not like there's some fixed threshold that we require for this constant.
Hello. Hey. Thanks for the nice talk. I was just wondering about your here. Sorry. About your desiderata, right? So you said at the beginning that it's not about the size of the circuit that you consider; it's about pumping out entropy. And then you had this two things about no fresh ancillas and no partial measurements in the middle. Yeah. Have you considered that there may be some kind of a continuous connection between actual BQP and the NISQ that you studied? That, for example, you can bring one ancilla per qubit or half an ancilla per qubit, and at some rate you will get to BQP or something like that?
Yeah, I mean, that perfect question. Yeah, so this is sort of when I say like a hierarchy between NISQ and BQP, that's exactly the kind of thing I would dream of, but unclear what the exact
thanks.
quantitative things are.
So here, with these oracles, did you also think about what happens if you implement them with noisy circuits? So if the oracles are actually noisy?
So I guess the negative results for so this kind of simple separation between that I showed at the end with this non-robust Simon's oracle. and also for the shadow tomography thing that I didn't have time to go into. In some sense, that's only capturing, whether or not you have noise like before and after the circuit implementing the oracle. Even like in some sense, just having that level of noise is already enough to break a lot of the speed ups that you get with full quantum. But yeah, I think it's an interesting question for maybe these the positive results in this work. Trying to understand that question is a great direction. Yeah.
Thanks.
So last question, and then we go for coffee break or offline questions. Okay.
I'm just, it's very related to the previous question, because in your model, you've got your NISQ circuit, and your oracle has to operate in superposition and can be very complicated. So it's a kind of model which is not relevant for current technology. It's sort of, okay, I've got some part which is, and some part which maybe your Bernstein-VAZIRANI oracle, which is not.
Yep.
And so, is there any way to hope get some separation which is closer to what can actually be done?
Right. So I guess the question, this is really applicable to the positive results in this work. So for instance, Bernstein-VAZIRANI and this separation between BPP and NISQ. In fact, the oracle separation between BPP and NISQ is, the amount of structure you need in the oracle is even more extreme. So I think this is all tied to this question. I don't know the answer. Like if you can design, more natural oracles that don't essentially wrap existing oracles around some error correcting code and still get some meaningful speed up, that could be a good starting point. But it's not clear. I don't know whether this is possible or not.